Welcome to the Jupyter Notebook session on bond structure theory. So today we are going to do some computational exercises focused on understanding the electronic structure in systems that have translational symmetry. And in particular, we are going to focus on one-dimensional and two-dimensional systems. And for this, we are going to use bond structure theory. So let us start with the first exercise, which is a one-dimensional chain. So the idea here is that we are going to look at a 1D chain of orbitals and compute the dispersion that we get in this case. So the way this works is that we define a chain geometry, and then we define a function that it's going to plot the unit cell just for visualization purposes. We first plot the unit cell of our geometry, and then afterwards we compute the band structure. And so the way that we compute the band structure is we generate first the Hamiltonian object. From the Hamiltonian object, we get the band structure in a default k-path, and then we plot the band structure as a scatter plot. And when we do that, we get these two plots. The one on the left is the geometry of the system, and the one on the right is the band structure of the system, in particular of a one-dimensional chain. And so now we can start with the exercise. So we need to identify what is the unit cell in the plot above, and the unit cell is just this side. So we have a chain with a single side, and therefore the unit cell has just one side. Then the next question is, what is the functional form of the band dispersion? And so if you look at this, you see that it's a cosine-like form, which is precisely the functional form that you get for the electronic dispersion in a one-dimensional chain with first neighbor hopping. And then the next question is how the density of states looks like. And so the way to compute the density of states is just by using some of the built-in functions. So we can start running this. So we first run the whole example to see our geometry and the band structure. And now we can compute the density of states. So to compute the density of states, we can do something like this. So get DOS, and with the default parameters, and we plot the density of states. And now we do it as a new plot. So now instead of having two plots, we are going to have three plots, which will look like this. So this is our density of states. And if you want to, let's say, have it a little bit more converged, you can just increase the number of K points. So we can say something like 400 K points. And now you see that it's a bit smoother, and we can even go to higher to make it even more smooth. And maybe what's interesting is actually to switch the axis of the density of states so that the energy is in the y-axis. So we can do this just by, let's say, transposing our plot. So now our x label is going to be the density of states, and our y label is going to be the energy, very much like in the band structure. And so it can be a good idea to put the same limits as our bands. And so we can take, let's say, for example, from -2.2 to 2.2, and we do the same in the bands. And now you see that what is the correspondence between the band structure and the density of states. So in particular, you see that in the band structure, we have some parts that are a little bit flat. So it's the top part and the bottom part. And in this part, we have a divergence of the density of states, whereas at intermediate energies, the dispersion is linear. And in those cases, we have a density of states that is a little bit flat. You can even increase the number of K points further if you want to have a little bit more converged result. And so the whole idea is that the density of states reflects what is the band structure of the system. And this happens also if you change the dispersion of the band. So something that you can do, for example, is now add second neighbor hopping. And so if you add second neighbor hopping, you see that your bands are changing substantially. And in particular, now you have a flat band over here that gives rise to a divergence, and then the band becomes, let's say, wider in the other direction. So your density of state remains roughly constant there. Okay, so now let us move on to a slightly more complicated example, so which is a one-dimensional chain, but now that has several sides per unit cell, so not a single side. This is what we call band folding. And so the whole idea is that we are going to take an initial chain and we make a supercell with two sides per unit cell. We plot the unit cell, and then we compute the Hamiltonian and we plot the band structure. And if we do that, we get the following plot. So here is your structure, here is the band structure of the system. Um, and so let us go with the first question. So the first question is, how is the block Hamiltonian for two sides per unit cell? And the answer is that this is a 2 by 2 matrix, that it's only off diagonal, so the diagonal elements are 0, and what you have in the off diagonal is just 1 plus e to the ik, because these are the hoppings that you get between one side and the neighbors. And then the next question is to take a bigger unit cell and see how the band structure is. And so what we can do here is first to look at a case of a single site per unit cell, just to remind ourselves. So this is the same cosine dispersion as we saw before. If we now take 2 sites per unit cell, we get 2 bands. If we take 3 sites per unit cell, we get 3 bands. And if we take 4 sites per unit cell, then we get 4 bands. So the more sites per unit cell we take, the more bands we have. And the reason for this is that the dimensionality of the block Hamiltonian is linearly proportional to the number of orbitals that you have per unit cell. And so in particular, if you have 4 orbitals per unit cell, your block Hamiltonian is a 4 by 4 matrix, and a 4 by 4 matrix has 4 eigenvalues, and that's why you see 4 bands. Okay, so let us now continue with the next example, which is a one-dimensional ladder. In particular, we are going to look at band folding in this one-dimensional ladder. And so in this case, we are going to take a slightly different geometry. So now it's a ladder instead of a chain. And we are going to do a loop through different supercells. So for each supercell, we create a supercell, and then we plot the band structure by first computing the Hamiltonian and then computing the bands. And we do this for different replicas. And so if we have a ladder just with 2 sites per unit cell, we get these 2 bands. If we have a ladder with 4 sites per unit cell, we get 4 bands. If we have a ladder with 6 sites per unit cell, then we get 6 bands. So let us go now to the examples. So the first one is, what is the dimension of the block Hamiltonian in each case? It is very easy, right? So here the dimensionality is 2, 4, and 6. Then the next question is, well, replace the ladder by a square ribbon, and what's the dimensionality of the block Hamiltonian in that case? So this is what we have to do here. So we are just going to now use a square ribbon instead of a ladder. And so we use a ribbon that has 5 sites per unit cell. We are going to get 5 bands. We have 10 sites per unit cell, 10 bands. And we have 15 sites per unit cell, 15 bands. And of course, it is something that you can scale to bigger and bigger systems. So now you make your ribbon wider. So 10 sites per unit cell, you get more bands, and even more bands. So in the limit in which you have a very, very wide ribbon, you are going to have a continuum of bands, and you are going to recover, in a way, a 2-dimensional electronic structure. Okay, let's move on to the next example, which is a 1-dimensional chain with long-range hopping. And so in this case, what we are going to do is we are going to take a chain and now not only include first neighbor hopping, but also third neighbor hopping. And so the way we do this is the following. We create first the geometry, then we are going to create a list of the third neighbor hoppings that we want, and we generate the Hamiltonian for each hopping combination that we want. And in particular, we want first, second, and third neighbor hopping. What we give is just this input to the TIJK keyword in the get Hamiltonian. So the first neighbor hopping will be 1, the second neighbor hopping will be 0, the third neighbor hopping will be T3. And so we get the bands for each case and we plot it. And so this is the result that we get. So for third neighbor hopping equal to 0, we get our cosine like band. For third neighbor hopping 1/3, we get this band that suddenly has a flat part here. And then for bigger T3, we get a more complicated band structure with several inflection points. And then the next thing that we can do is to compute the density of states. So this is the identical system as before, but now instead of computing the band structure, we compute the density of states. So this would be the density of states with third neighbor hopping equal to 0, with third neighbor hopping 1/3, with third neighbor hopping even bigger. And so the whole idea now is the following. So let's go with the exercise. So how is the divergent density of state related with the band structure? And so this idea is very simple. So we have a divergence every time that there's a band that it's flat, right? And this is something that we can check here. So let's recompute it just for our sake. So in this case, with T3 equal to 0, we have a flat band at 2, and at -2. And now if we go to the density of states, we see that we have a divergence at -2 and a divergence at 2. This is the very same idea as what we saw at the beginning. If we now look at this case of T3 equal to 1/3, what we actually have now is that the band is flat over here, over there, in particular at charge neutrality, and then at the bottom of the band. So what this means is that now we are going to have a divergence at the bottom of the band, right in the middle, and then at the top of the band. And if we look at the case in which T3 is even bigger, we have a flat part over here, over there, over there, over there, over there, over there, and over there. So when we compute the density of states, we'll see divergences at all those points. Now, why do we get a divergence at energy equal to 0 for T3 equal to 1/3? And the answer to this is that at that specific value of T3, the Fermi velocity at energy equal to 0 becomes 0. So you get a flat band, and the emergence of this flat part of the dispersion gives rise to the divergence. And then the last question is, if instead of third neighbor hopping, we had second neighbor hopping, how would the band structure change? And so to do this, we can just change third neighbor hopping by second neighbor hopping. So we can just, transform T3 now into second neighbor hopping, and we are going to change the label. Also, for clarity, we transform the T3 in second neighbor hopping, and we change the label, and we get the following. So for T2 equal to 0, we get the same. For a finite T2 equal to 1/3, we get that there's a flattening over here, and this can be seen in density of states as a very much enhanced divergence. And then we even increase more T2, we get this strongly asymmetric dispersion, and this is what we observe here with two Van Hoff singularities. And so one of the important consequences is that now the density of states is very asymmetric in energy. And this appears because the existence of a second neighbor hopping breaks the bipartite nature of the lattice, and in particular breaks chiral symmetry. Okay, then let's move on with the next exercise, which is about a two-dimensional graphing. So in this case, we are going to take a honeycomb lattice, or we are going to plot the unit cell, we generate the Hamiltonian, we compute the band structure, we plot the band structure, we compute the density of states, we plot the density of states, and we get the result below. And we can recompute it right now just to see. So we have a honeycomb lattice with two sides per unit cell. So our block Hamiltonian is a 2x2 matrix. When we diagonalize this Hamiltonian in a certain path in the Brillouin zone, that is the gamma k m k prime gamma path, we get these bands. And in particular, these 2 points over here are the Dirac points. These are the points in which if we do a Taylor expansion to the block Hamiltonian, we recover a two-dimensional Dirac equation. And then if we compute the density of states of this system, we get exactly this. So the first thing to notice is that you have Van Hoff singularities at -1 and +1. This stems from this flat part over here and flat part over there. And then at low energies, you have a V-shaped density of states. Okay, let us look at the exercise. So the first one is to identify the unit cell, and this is what we did before. We have two sides per unit cell. And the next one is to replace the honeycomb lattice by a Kagome lattice or leaf lattice. Okay, so let's first do the leaf lattice. So the leaf lattice is effectively a square lattice in which you remove 1 out of 4 sides. So you have a unit cell that has 3 sides per unit cell, and therefore it will have 3 bands. And in particular, the band structure that you get is this one. So you get a band that is completely flat, right at charge neutrality, and the 2 bands that are heavily dispersive. And so if you look at the density of states, what you actually get is something like this. So you get a peak at 0 energy that comes from this flat band over here, and then you get this Van Hoff singularities at -2 and +2. And so this is actually a very interesting lattice because it has a flat band, and every time that you have a flat band, you have a very large density of states, and therefore interactions are going to create a very big impact on it. And the leaf lattice is not the only lattice that has that feature. So there's another lattice that is the Kagome lattice. Also looks very much like that. So the Kagome lattice is effectively a triangular lattice, and it arises if you remove one of every four sides in a unit cell of the triangular lattice with four sides. So the unit cell has three sides, and therefore this will give rise to three bands. So you get a flat band over here and then these bands over there. And the interesting thing to note is that this band structure over here is very, very similar to the one of the honeycomb lattice. So it has direct points over here and over there. And then on top of that, you have this flat band at the very bottom, which appears due to the frustration of the lattice. So if you look at the density of states of this lattice, what you see is the Van Hoff singularity at -2, and then very much the density of states of the honeycomb lattice shifted a little bit in energy. And so the Kagome lattice is also a very important lattice due to this coexistence of Dirac points over here and flat bands over there. Okay, so then let's move on. So something interesting to note is that the band structure of a two-dimensional system depends on which direction in the Brillouin zone you take. So in particular, you can take two potential directions, or I mean, there are many paths in the Brillouin zone, but in particular, you can take a path that it's gamma k m k prime gamma path, or the gamma k m gamma path. And so if you go in this path, you will pick the two Dirac points of the honeycomb lattice that are located at k and k prime. If you go in this path, you will only pick the Dirac point that is at the k point. And so the Dirac points are precisely here and there. And this is, of course, something that happens also with the Kagome lattice. So if you replace the honeycomb lattice by a Kagome lattice, you will see something very similar. So in the first path, you pick the two Dirac cones. In the second path, you just pick one of the Dirac cones. Yeah, now you have Kagome lattice for both of them. Okay. So then the next point is that in certain cases, we may actually want to see the band structure in the whole two-dimensional space at once. And this is, of course, something that we can do just by doing a heat map of the two bands. So in particular, if we do it for the honeycomb lattice, we get these two plots. So this is the valence band, and this is the conduction band. And so what you actually observe is that the valence band peaks at this hexagonal points in the Brillouin zone, the conduction band the same, and in particular, these points in the Brillouin zone correspond to eigenvalue 0, both for valence and conduction band. So these are precisely the Dirac points of the electronic structure. So this is the answer to the first question, and then next question is to replace the honeycomb lattice by Kagome lattice and see how those maps look like. So we can just replace here honeycomb by Kagome. And so in the Kagome lattice, we get these two maps. So the first one is completely flat. So we see absolutely no change whatsoever. And then the second one is like this. And so the reason for this is that this is precisely the flat band, and this is the second band of your electronic dispersion, meaning that the first plot corresponded to this band that didn't disperse at all, and then the second plot corresponded to this band that dispersed quite a bit. And so, of course, we may want to just plot the two bands that have dispersion, and for that, we could just do the following. So in this case, now we see that the two bands have a certain dispersion, and both dispersions meet at these points in reciprocal space that are precisely the Dirac points of the dispersion. Okay, let us move on to the next exercise, which is the case of a Fermi surface for the honeycomb lattice. And so the whole idea is that now we can try to see all these eigenvalues in a slightly different way. So instead of plotting all the energies at once, what we are going to do is we are going to select a certain energy and plot which points in the Brillouin zone have an eigenvalue at that energy. This is the definition of the Fermi surface. And so what we do is we generate a honeycomb lattice, we generate the Hamiltonian, and then we generate the Fermi surface, which, as I mentioned before, is a collection of points that have an eigenvalue at a specific energy. And so we select the energy with E. And then this function automatically will give you a two-dimensional heat map. So we can execute this and see how the Fermi surface looks like. So at energy 0, we see that only these points in reciprocal space will have an eigenvalue, and this corresponds exactly to the valleys, to the k and k prime point. And as we increase the energy, we see that the Fermi surface is going to grow, and it will create some sort of distorted circle around the k and k prime points. And as we increase the energy, the circle will grow more and eventually merge. And this is the point in which we have the Van Hoff singularity. So you see here that there's a very large number of points in reciprocal space with identical eigenvalue. And in particular, there's nesting, meaning that one can find one vector that connects many different points in reciprocal space right at the same time. And then if we keep increasing the energy, then these two Fermi surfaces will merge and will give rise to a circular Fermi surface around the gamma point. And so one of the important points to notice here is that we go from a situation in which there are two Fermi surfaces to a situation in which there's a single Fermi surface, and this is what it's called a Lipschitz transition. So now let us go to the question. So identify at which energy the Van Hoff singularity appears. So the answer is at energy equal to 1. Then we need to compute the Fermi surface at higher energies and see how many pockets we have. So for this, we can just increase the energy over here. So instead of going just to 1.3, let's go to 2.3. And then we do this, we will see that if we keep increasing the energy, then this Fermi surface is going to shrink and shrink. And eventually, when the energy is very big, it will become just 1 point. And afterwards, we will be away from our bandwidth. And then the next question is replace the honeycomb lattice by a square lattice and see how the Fermi surface now. So we just replace by a square lattice. And now in this case, we see that the Fermi surface is actually very different. So at charge neutrality, we have this merging of two Fermi surfaces. So the square lattice at charge neutrality actually has a Van Hoff singularity. And then as we increase the energy, then the Fermi surface starts shrinking and shrinking and shrinking. And so something interesting of the square lattice is that we can try to play this game of going from negative to positive energies and see what happens at the intersection. So if you start with negative energies, you have pockets around the corners of the Bernoulli zone. If you increase the energy, the pockets start growing and eventually they merge. And after merging, then you get pockets around the gamma point. And so this is, again, called a Lipschitz transition. So you go from pockets in one point in the Bernoulli zone to pockets in the other Bernoulli zone, and you pass by a phase transition in which your Fermi surfaces merge. And of course, we can do this with many other lattices. So we could do it, for example, with a triangular lattice. And so with a triangular lattice, we are going to recover a hexagonal Brillouin. So at energy -2, we actually have our Van Hoff singularity. And then as we increase the energy, then the Fermi surface is going to become smaller and smaller and smaller and smaller. If we want to see the Lipschitz transition, what we can do is to plot this in a wider energy range. So if we start over here, we have a situation in which there are two pockets. Then the two pockets will merge and eventually will give rise to a single pocket. Okay, then let us move on to the density states of the honeycomb lattice. So what we are going to do now is we are going to take a honeycomb lattice, compute the Hamiltonian, compute the density states, and plot the density states. And so we first exercise to identify the location of the Dirac points in these density states. And the answer is that the Dirac point is precisely over here. It's in this V-shape part of the density states. The Van Hoff singularities are right at -1 and 1. So these two peaks over there. And then the next question that is the most interesting one is to replace the honeycomb lattice by a triangular lattice and see if we still have Dirac points. So now we use a triangular lattice. In this case, you see that there's no part in which there's a V-shaped density of states. And if we wish to plot it in a wider range, we can do the following. So we can do this, and you see that no matter where you look in energy, there's no V shape. So there's no Dirac point in the triangular lattice. If you do it in the Kagome lattice, Then in the Kaloma lattice, you do have a Dirac point. So you have this point over here that has a V-shape density of states that maybe it is even easier to see if you restrict the limit of the plot. So we can just plot it from 0 to 2. And if we plot it from 0 to 2, you will see that we will actually see that there's certainly a V-shape density of states. So now you perfectly see the V-shape density of states. And if you look at other lattices, for example, the square lattice, you will see that in the square lattice there's also no Van Hoff's there's also no Dirac point. So there's a Van Hoff singularity at energy equal to 0 that you can, let's say, very easily see if you choose a symmetric range for the energy. So now you see your Van Hoff singularity, but there's no V-shaped density of states anywhere. So the honeycomb lattice and the Kagoma lattice are in a way special because they have this V-shaped density of states, and that V-shape is associated with a Dirac point. Okay, let's move on to the next exercise, which is about the bond structure of honeycomb nanoribbons. So now we are going to take one-dimensional geometries, and in particular one-dimensional geometry that have a certain width and made of a honeycomb lattice. So we first create an armature ribbon, we plot the unit cell, we get the Hamiltonian, we compute the bands, and we plot the bands. And if we do this, we get the following. So this is our unit cell. So we have 4 sides times the number of rows per unit cell, and this gives rise to this band structure. So you have as many bands as red dots you see over here. Okay, so that's the answer to the first question. And then the second question is, what happens if we change the width of the ribbon? And in particular, how many bands do we have if we change the width? And so to do this, we can just replace the width of the armature ribbon. So we can start with 1. So we have with 1, we have just 4 sides per unit cell. This gives rise to 4 bands. If we have a width 2, then we have more sides per unit cell and therefore more bands. And if we now take a very, very, very wide ribbon, then we are going to have many, many bands, and eventually we are going to have a continuum of bands. And so the next question is to replace the armature nanoribbon by a zigzag nanoribbon and see what is the difference between the two. And so we can just use this honeycomb zigzag ribbon geometry. And the difference is that now in the zigzag geometry, you see that there's a flat band over here. This flat band did not exist in the case of the armature geometry. And this flat band is appearing because states get localized at the edges, in particular, right at the top and right at the bottom. And this flat band is going to give rise to electronic instabilities. Okay, now let us move on to the density of states. So we are going to continue with nanoribbons, but now we are going to look at the density of states instead of at the band structure. So we are going to start with a armature nanoribbon. We plot the unit cell, we get the Hamiltonian, we plot the density of states, and we get this. So this is your unit cell, this is the density of states, and in particular, you see that something like a V shape with some peaks appears here. Let us look at the question. So the first one is, why are there several divergences in the density of states? And the answer to this is that if you look at the band structure of our armature ribbon that we can do again with the previous example, you will see that there are many bands that get flat at some point. So first over here, first over there, then over there, and so forth. And so every time that you have a band that it's a little bit flat, that will give rise to a specific peak. And in particular, the number of peaks increases with the width of your ribbon. So if you take a relatively narrow ribbon, you are going to have a small number of Van Hoff singularities. If you take a wider ribbon, then you are going to have a bigger number of Van Hoff singularities, and eventually, of course, they are going to merge and create a continuum. So this is actually something that very easily allows you to see the appearance of the thermodynamic limit. So this is a ribbon with width 20. If you go, for example, to width 50, you will see that you get nearly the bulk result for the density of states of graphene. So you see that you get this almost perfectly continuous density of states. Okay, so now let us look at the width dependence of the electronic structure a little bit more in detail. So we are going to create geometries of armature ribbons with different widths, get the Hamiltonian, get the bands, and plot them. And so this is what you see over here. So as you increase the width, the number of bands increases, and in particular, your gap is also changing. So for you have gap, gap, gapless, gap, gap, gapless, and this type of alternation. And you can see this evolution also in the density of states. So you see density of states in the first case, so gap, gap, gapless, gap, gap, gapless, and so forth. And so the first question is if you can infer which ones are gapless. And so the answer is that every 3 widths you get a gapless system. So first one gap, one gap, one gapless, one gap, one gap, one gapless, one gap, one gap, and the next one would be gapless. And this actually appears due to the folding of the electronic structure when you consider a one-dimensional nanoribbon. And then the next question is if you can infer what is the evolution of the gap of the system as a function of the width. And then, of course, the trick here is that one needs to look at systems that have gap all the time. And in particular, one would need to look at 3n systems in order to factor out this oscillation. And so the solution to this is that if you make a plot of the gap as a function of the width, you will get a power law dependence, and in particular a 1/L dependence if you go every 3 widths, because you have a Dirac equation. Okay, let's now continue with band structures and interactions. So we are going to see how the impact of interactions changes our electronic structure. So for this, we are going to take a honeycomb lattice, generate the Hamiltonian, generate a mean field Hamiltonian first with u equal to 0, and get the bands, and then do the exact same thing, but now with interactions. And so let's do it. So we don't have any electronic interactions. Our system becomes gapless in the case of honeycomb lattice, and then if we have interactions, then we get a certain gap. Then the first question is, well, what happens if we decrease the value of the interaction below 2? So for this, we just replace the value of u by a smaller value. And in this case, you see that now the system is gapless. If we take a very large value of u, then the gap is going to become very big. Okay, so now we are going to look at this more systematically. So we are going to generate our honeycomb lattice and do self-consistent calculations for different values of u. And we are going to go from 0 to 4 in small steps. So we are going to do mu-fin calculation, then compute the bands, and we plot the bands. And this is the result that you see over here. So for u equal to 0, system is gapless, 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 and suddenly the gap opens up. So the gap opens up somewhere in between 2.2 and 2.8. And so the first question is to find the critical value of u that gives rise to the gap opening. So to do this, we could just do a finer mesh between 2 and 2.6, for example. And then when you do the calculation, you can just see at which value exactly the gap appears. And you see that the gap starts appearing as something like between 2.3 and 2.4. So that's where the critical value of u for the Hubbard model in the honeycomb lattice at mean field is located. And then the second question is, what is the symmetry breaking that gives rise to such gap opening? And so the solution is that the symmetry breaking that appears is an antiferromagnetic ordering, because that is the one that is promoted by on-site interactions if you don't have anything else at half filling in a bipartite lattice. Okay, so now let's continue with interactions, but now in nanoribbons. So instead of doing 2D, we are going to do 1D, and we are going to take a zigzag ribbon that had these flat bands that we were discussing before. So we make a certain supercell, we generate the Hamiltonian, we generate the bands, we generate the local density of states. And so the idea here is that if we plot the local density of states at energy equal to 0, we will precisely see what is the location of the states. And you see that at energy equal to 0, all the states are located at the edges, at the upper edge and at the lower edge. And so this is the answer to the first question. And then the next question is, well, when interactions are included, which states are going to be affected the most? And the answer is that if your chemical potential is at 0, then these states living at 0 are the ones that are going to be affected the most. And this is what we are going to see now. So we are going to take a zigzag ribbon again and do a mean field calculation, first with ferromagnetic initialization, second with antiferromagnetic initialization, and see what is the result. So you see that regardless of whether if you converge to a ferromagnetic solution or antiferromagnetic solution, the biggest difference appears in the edge state. So in one case you get a gapless system, in the other case you get a gapped system. And so now the first question is, well, if we get two self-consistent solutions, which one of them has the lowest energy? So the system must have one true ground state, and clearly ferromagnetic and antiferromagnetic are inequivalent ground states. And so one could, of course, compute the total energy of the system, but an easier way instead of that is just by seeing that one of them is gapless and the other one is gapped. And so in general, if you open up a gap, the total energy of the system is going to be lower because, of course, when you sum all the eigenvalues, you're going to get a slightly smaller number. And so with that criteria alone, we can see that the system that has a gap will have lower energy. Okay, so now let us go to unfolding band structures, first in a one-dimensional chain with impurities. And so the whole idea is that when you make supercells, your bands get folded, but in certain instances, you may want to go back to the original band structure in the smallest unit cell. And so the way we do this is we create a chain, we create a certain supercell, then the Hamiltonian, and then we compute the bands with a certain operator that's an unfolding operator. That's an operator that allows you to project the band structure back on the original unit cell. And we are going to do this without any impurity per unit cell. So this would be effectively a completely pristine system, and then with an impurity per unit cell. And so these are plots that we are going to get. So without an impurity, you see that you get, let's say, a single cosine band after doing the unfolding. So in the full unit cell, you would get this folded band structure. And with an impurity, you get a cosine band, but that it gets broken at different momenta. And these momenta at which the band gets broken are the momenta in which you get mixing between the different bands of the supercell. Okay, so now let us first recompute the band structure for their system sizes. So let's use a system size that is bigger. So instead of 4, let's take, for example, 6. And so if you do that, you will see that the unfolded band structure is identical, but the unfolded band structure with an impurity has more anti-crossings. And of course, if you make the system bigger and bigger and bigger, you will have more and more anti-crossings. And so, for example, if you take a system with 20 sites per unit cell, you will get, let's say, many anti-crossings here that you can actually see even better if you increase the size of the impurity that you add here. So we can, for example, put an impurity of 2.5, and you will see now that there's, let's say, many more anti-crossings. Okay, so then the next question is to take a very large value for the impurity potential and see what happens to the band structure. So let's take a moderate system size, for example, 6, and let's start with a small value of V. So with a small value of V, you get these small anti-crossings in the band structure. Now you can start increasing the value of V, for example, to 1.5. And with 1.5, you see that the anti-crossings become actually bigger. And if you go to a really big value of V, you see that your bands become almost flat and your anti-crossings become very big. So what is happening here is that as you make the impurity very big, you are effectively breaking your lattice. So electrons are not able to propagate anymore, or not as easily as in the case with the absence of an impurity. And then the third question is to replace a chain by a ladder and choose a large value of V. See what we observe and why. So for this, let us take first the ladder, and we are going to first use a moderate value of V, right? So with 0 value of V, we get our band structure of the pristine ladder after doing the unfolding. And then with an impurity, we see that we get bands that have some small anti-crossings at different momenta due to the impurity. Now, if we start increasing the value of V, we see that anti-crossings appear. But even when we take very, very large values of V, we still have a sizable dispersion. And so the reason for this is that in the ladder, even if you take a very large value of V, you are not breaking your system because the electrons can still propagate through the other arm of the ladder. And so that's why you still have a sizable dispersion even in the presence of a large impurity. Okay, and now let us look at a different case. So we are going to look at what happens if we put impurities in a two-dimensional system, in particular in a honeycomb lattice, in the honeycomb lattice of graphene. So we are going to take a honeycomb lattice, we generate the Hamiltonian, we add an impurity, and then we are going to solve this system actually using an embedding method. So this method effectively allows you to solve a system that it's infinite and with a single impurity. This is very different from Bloch's theorem, but in practice allows you to solve single impurities in infinite systems. So without a vacancy, we get our V-shaped density of states. With the vacancy, we get this, let's say, very sharp peak at zero energy. So in the honeycomb lattice, when you put a vacancy, you actually get a zero mode. And so what we can try to do now is instead of putting a vacancy, just to put a very large finite potential and see what happens to the density of states. So what we can do now is just to use a potential that it's 10, for example. And in this case, you will see that the zero mode is no longer a zero mode, but actually gains a finite energy. So this is what happens if you do that. So you get a peak in your density of states that it's not exactly at zero energy, but it's close enough. And the idea is that as you make your local potential bigger and bigger and bigger, then this peak is going to move towards zero energy, and it will become effectively your vacancy state. And then in the case above, you can check what happens if you change the sign of the potential. And so instead of using V plus 10, you take V minus 10. What actually happens is that your whole spectra gets inverted. So instead of having a peak that it's a little bit below zero, you get a peak that it's a little bit above zero. And then, of course, when you go to the limit in which you have an infinite potential, it truly doesn't matter if it is positive or negative because that side is completely forbidden for the electrons. Now, so something that you can do is to plot actually how that state is located in space, and that can be done by computing the local density of states. And so when you do that, you get this plot. So the impurity is put right here in the middle, and you see that the local density of states at zero energy is effectively concentrated on these sites around your missing site, and of course it leaks a little bit towards those sites. And so the first question is to change the energy of the local density of states and see how the profile changes. And so we can take a larger energy. So for example, we can take something like 0.5, which no longer has the local density, the zero peak. And so this is something that we can change over here. And so if you do that, you see now that at energy 0.5, then the states are everywhere. So they are no longer located at this special site, but they are just bulk states. And then the next question is to replace the infinite potential by a finite potential, then for example, and see how the profile changes. So if we take, for example, a profile minus 10, and we go back to energy equal to 0, then you see now that the state is fairly delocalized, right? And this is because at energy 0, we are roughly over here. If we take, for example, energy 0.1, we should see a state that it's much more localized. And this is something that we can very easily do. So we take energy 0.1, we see that the state is more localized. And if we had taken energy minus 0.1, we would have gotten a very delocalized state. Okay, so now let us move on to looking at impurities in a superlattice. So instead of considering a single impurity in an infinite system, we are going to consider an array of them. So we are going to start with a honeycomb lattice. We make a certain supercell of size n. We generate the Hamiltonian, and we are going to compute the band structure of that Hamiltonian with the unfolding operator. And we are going to do this first without an impurity and then with an impurity. So if we do it first without a vacancy in graphene, we get our unfolded bands that are precisely the band structure of the honeycomb lattice. And then if we have a vacancy, our unfolded bands are going to be the ones of a honeycomb lattice with many anti-crossings, and what is most important with these zero energy modes right at charge neutrality. So let us look at the question. So the first one is to recompute the band structure above for other supercell sizes. So let us start with a smaller size. So we do first a 2x2 unit cell. Without an impurity, we recover the original bands. And with an impurity, we get something very, very different from graphene, right? This is because if you just remove one side in a small unit cell, then you get something that is very far from a honeycomb lattice. And then as you make your system bigger and bigger and bigger, you recover a band structure that it's, let's say, more similar to the one of graphene. So with a 4x4 super lattice, you already get an unfolded band structure that resembles the one of graphene plus zero modes. And then if you take an even bigger unit cell, then your band structure is going to resemble even more what the band structure of graphene is, even in the presence of an impurity. And this, of course, happens because as the unit cell gets bigger and bigger and bigger, the impurity affects the whole system in a smaller and smaller way. So this is with the 6x6 unit cell, and you see that, well, you get almost the same as in the pristine case. Okay, so then let's move on to the second question, which is take a large finite value for the impurity potential and see what happens to the flat band. And so the whole idea is that we are going to emulate what we were doing before with a single impurity in a system. So let us take first moderate unit cell, so a 4x4, and replace the large potential by a moderate potential, let's say, for example, 5. And so if you do that, you will see that you no longer have a perfect flat band at zero energy, but you have something at zero energy that has a little bit of dispersion, right? And if you now start increasing the value of V, so if you now go to V25, you will see that the band becomes flatter, not completely flat, but that it starts resembling what we knew from a single impurity in an infinite system. And so this is everything for today. Thank you so much for joining, and see you next time.